Dear students, in this lecture we discuss theory of linear homogeneous differential equations. The equation is given by L of y equal to 0, that is, we know that L of y is nth derivative of y plus some constant, some function p1 of x into n minus 1 order derivative of y plus and so on plus p n minus 1 of x y dash plus pn of x y equal to 0. When right hand side is 0, then we call it as homogeneous equation. First result is principle of superposition. So this result says that if we have number of solutions to this differential equation, then their linear combination is also a solution. If y1, y2, and so on, yn are solutions of differential equation L of y equal to 0, then the linear combination C1y1 plus C2y2 plus and so on Cnyn is also a solution for any values of the constants C1, C2, and so on Cn. Okay, so this result says that for any set of solutions y1, y2 to yn, their linear combination. Okay, such a representation C1 y1 plus C2 y2 plus and so on Cn yn with constants C1, C2, and so on Cn. So this expression is called as linear combination of solutions y1, y2 to yn. This result says that if y1, y2, and so on yn are solutions, then any linear combination of these solutions is also a solution. Let us see the proof. So given that y1, y2, and so on yn are solutions of L of y equal to 0. So this shows that L of yk is 0 for k equal to 1, 2 and so on n. Okay, if these functions are solutions, this should satisfy that differential equation. We call this as 1. Define y equal to c1 y1 plus c2 y2 plus and so on cn yn, where ci's are constants. We want to show that this y is solution. Okay, our claim is this y is solution. That means L of y is 0 for this y. Consider L of y, that is L of c1 y1 plus c2 y2 plus and so on plus cn yn. Now we have seen that L is linear operator because the derivative is linear operator. Okay, so this becomes c1 into L of y1 plus c2 into L of y2 plus and so on plus cn into L of yn. Now using one is L of yk is 0 for each k. That means L of y1 is 0, L of y2 is 0 and so on. L of yn is 0. So this is 0. Okay, so what we have shown? We have shown that L of y is 0. This means y is solution, and this proves the result. The converse of this result is true under certain conditions. Okay, so for that we need a concept of Wronskian. Wronskian of set of solutions is a determinant. So let us see the definition. Let y1, y2 and so on yn be the solutions of differential equation L of y equal to 0. The Wronskian of y1, y2 and so on yn is the determinant given by W of y1, y2 and so on yn. Okay, this is notation for Wronskian, and it is the determinant whose first row is y1, y2 and so on yn. Second row is derivatives of first row elements, that is y1 dash, y2 dash and so on yn dash. Third row is y1 double dash second derivatives and so on. We continue up to the derivative of order n minus 1. So y1 n minus 1 order derivative, y2 n minus 1 order derivative, and so on, yn n minus 1 order derivative. Okay. So this is n by n matrix. So we can have determinant, and it can be evaluated at any point x in the domain. Now we are ready to see the converse of superposition principle. So result is, if the functions, so there are three conditions. If first condition is the functions y1, the coefficients in the given differential equation L of y, that is p1, p2, and so on pn, are continuous. Okay, continuity is necessary condition for existence and uniqueness, as we discussed earlier. Continuous on the open interval I. Second condition is on the solutions, the functions y1, y2, and so on yn are solutions of homogeneous differential equation L of y equal to 0. And third condition is Wronskian of all these functions y1, y2, and so on yn at any point x in interval I is non-zero for at least one point x in I. Okay, so all these are the conditions. If the functions p1, p2 to pn are continuous, second thing, y1, y2, and so on yn are solutions, and third thing is Wronskian of these solutions is non-zero at some point in interval I. Then every solution of L of y equal to 0 can be expressed as a linear combination of y1, y2, and so on yn. Okay, so the superposition principle was, if y1, y2, and so on yn are solutions, then their linear combination is also solution. Here, converse is, if we have any solution of L of y equal to 0, then we can express that solution as linear combination of these solutions y1, y2 to yn, satisfying certain conditions. The conditions are, first condition should be continuity of the coefficients in the linear differential equation. This is necessary for the existence and uniqueness of solution. Second thing is, these solutions y1, y2, these functions y1, y2, and so on, these should be solutions. And third is, Wronskian of these solutions is non-zero. Okay, the important condition is Wronskian non-zero implies we can have any solution in terms of linear combination of these solutions. Okay, let us see the proof. So we see the proof in two steps. So first we take any solution of this differential equation. Okay, so let phi be any solution of this differential equation L of y equal to 0 on interval I, open interval I. So we take any point in this interval, say x naught. Suppose for x naught in I, phi of x naught is some constant phi naught, phi dash x naught is phi 1, and so on. Phi n minus 1 order derivative at x naught equal to phi suffix n minus 1. Okay, so this phi is solution of L of y equal to 0. What we have done, we obtain values of phi and its derivatives at certain point x naught. Okay, so phi of x naught is some constant phi naught, phi dash of x naught is phi 1, and so on. Phi n minus 1 derivative at x naught is phi n minus 1. Now we take constants. So for unknown constants, okay, unknown constants C1, C2, and so on Cn, consider the linear system. So we consider the system C1, Y1. So this is important system. C1 into Y1 at point x naught. X naught is the same point which we consider here. Okay, x naught. C1 into Y1 of x naught plus C2 y2 of x naught plus and so on plus cn yn of x naught equal to phi naught. Second equation we consider c1 into y1 dash x naught plus c2 y2 dash x naught plus and so on plus cn yn dash x naught equal to phi 1, and we continue. So next equation will be c1 y1 double dash x naught plus and so on plus cn yn double dash x naught equal to phi 2. Okay, so continuing, we get the last equation c1 y1 n minus 1 order derivative at x naught plus c2 y2 n minus 1 x naught plus and so on plus cn yn n minus 1 x naught equal to phi n minus 1. We call this as system 1. Note that we know all these values y1, y2 and so on yn. So y1 of x naught will be a fixed constant value, y2 of x naught and so on, yn x naught. All these are known values. Right hand side phi 0, it is known. Similarly, in second equation also y1 dash x naught, y2 dash x naught and so on, yn dash x naught and phi 1, all these are known things. Okay, so in this system c1 c2 to cn are unknown, so we are saying that unknown constants. Okay, and we have to solve this system and find the values of c1 c2 to cn. That means we try to find the constant ci's satisfying the system 1. And from linear algebra, we can have a condition on this system to have unique solution. Okay, so let us write this system in the form of matrix. Okay, so this system is nothing but matrix y1 x naught, first row is y1 x naught, y2 x naught and so on, yn x naught. Second row is derivatives y1 dash x naught, y2 dash x naught and so on, yn dash x naught and so on. So last row is y1 n minus 1 at x naught, y2 n minus 1 at x naught and so on, yn n minus 1 at x naught. This matrix multiplied by column vector c1 c2 and so on cn equal to phi 0, phi 1 and so on, phi n minus 1. Okay, so system of equations 1 is same as this matrix equation. Okay, so this is of the form ax equal to b, where A is matrix and yn matrix, x is column vector in Rn, b is also column vector. So this system has unique solution if determinant of A is non-zero. Okay, if determinant of A is non-zero, then it is invertible. We can multiply this system by A inverse from left, so that it is A inverse A x equal to A inverse B. A inverse A is identity matrix, so x equal to A inverse B. This is unique solution of this system. X is column vector containing unknown terms. Okay, so here capital X is this C1, C2 to Cn. Capital A is this matrix and B means right hand side. Okay, so condition is A inverse exists. That means if determinant of A is non-zero, then we can have unique solution. Okay. If the determinant of coefficient matrix is non-zero, then there exists unique solution C1, C2 to Cn to this system. But what is determinant of coefficient? Determinant of this coefficient matrix is Wronskian. Okay, Wronskian at x naught. Okay, and given thing is Wronskian at x naught is non-zero. Okay, so this is second condition. Okay, so at least one point that is x naught. Okay, so we should mention it. Suppose for x naught in I, Wronskian y1 y2 to yn at x naught is non-zero. Okay, and here we write let phi of x naught be this. Okay, so since this determinant is Wronskian y1 y2 to yn at x naught and is non-zero, there exists unique solutions C1, C2 to Cn. Okay, now C1, C2 to Cn are known things. Okay, so from these constants we define new function using, so step 2, using these constants. Now these are known constants. Define function psi to be c1 y1 x. Okay, psi of x is c1 y1 x plus c2 y2 of x plus and so on plus cn yn of x. Observe that what is L of psi? It is L of c1 y1 plus and so on plus cn yn at any point x. And we know that y1, y2 and so on yn are solutions. So this must be 0. This means psi is solution of L of y equal to 0. Psi is solution of L of y equal to 0. Next thing, what is psi of x naught? Psi of x naught is c1 into y1 of x naught plus c2 into y2 of x naught plus and so on cn into yn of x naught. But this expression is nothing but phi naught. From first equation in system 1, this is nothing but phi naught. Okay, so psi of x naught is phi naught. Similarly, psi dash of x naught is c1 into y1 dash x naught plus c2 into y2 dash x naught plus and so on, cn into yn dash of x naught, and it is nothing but phi 1. And so on. Psi n minus 1 order derivative of derivative at x naught is phi n minus 1. So what this means? This means psi is solution of L of y equal to 0 satisfying same initial conditions as phi, because phi 0, phi 1 and so on, phi n minus 1, these are initial conditions satisfied by another solution phi. Okay, so these are same conditions. Phi of x naught is phi naught, phi dash x naught is phi 1 and so on. Okay. Psi satisfies same set of initial conditions as that of okay. So phi and psi both are solutions of L of y equal to 0. They are satisfying same initial conditions. Therefore, by existence and uniqueness theorem, both these solutions must be same, because existence and uniqueness theorem says that the solution to initial value problem should be unique, and we are finding two solutions to the same initial value problem. Okay, so phi and psi both should be same functions. Okay, therefore by existence uniqueness theorem, this phi should be same as psi. Okay, now by 2 psi is given by c1 y1 plus c2 y2 plus and so on cny. So the same expression should be for phi. Okay, therefore by 2 phi of x is c1 y1 of x plus c2 y2 of x plus and so on plus cn yn of x. What this means? In the first step, we have taken a solution phi, any solution phi to this homogeneous differential equation. Okay, so phi of any solution, and we have shown that there are constants c1 c2 and so on cn such that phi is c1 y1 plus c2 y2 plus and so on cny. Okay, so every solution of L of y equal to 0 can be expressed as a linear combination of y1, y2 and so on y. Okay, so important condition is Wronskian is non-zero. Okay, so we proved this result. We discuss some important terminologies now. So we have seen that if Wronskian of y1, y2 and so on yn is non-zero, then every solution of L of y equal to 0 can be expressed in terms of y1, y2, and so on, yn. Okay, so these are some fundamental things. Okay, so such solutions are called as fundamental. Okay, so fundamental set of solutions is the set of solutions for which Wronskian is non-zero. That means every solution of the problem can be expressed in terms of all these solutions. Definition: a set of solutions y1, y2, and so on yn of L of y equal to 0, homogeneous linear differential equation, whose Wronskian is non-zero. Non-zero means non-zero at some point. Okay, the result is that if Wronskian is non-zero at some point in the interval I, then it will be non-zero everywhere in I. So we are not going to discuss that result. So Wronskian is non-zero means at any point in the interval I is called as fundamental set of solutions. It is fundamental because every solution can be expressed in terms of these functions. And so such linear combination is called as general solution. General because every solution is in terms of these solutions. The linear combination of any fundamental set is any fundamental set of solutions of L of y equal to 0 is called the general solution. Okay, so if the differential equation is given and it is asked to find general solution, then we have to find fundamental set of solutions and take linear combination. Okay, that means C1 y1 plus C2 y2 plus and so on Cn y. Next definition: the functions f1, f2, and so on fn are said to be linearly dependent. Linearly dependent on an interval I if there exist constants C1, C2, and so on Cn, not all 0, such that C1 into f1 of x plus c2 f2 of x plus and so on plus cn fn of x is equal to 0 for all x in the interval I. Okay, so this set of functions f1, f2 and so on fn, it is linearly dependent if we can find constant c1, c2 and so on cn not all 0, such that this linear combination is 0 for all x. Next definition is linearly independent. Okay, so if the set is not linearly dependent, then it is said to be linearly independent. The functions f1, f2 and so on fn are said to be linearly independent if independent on interval I if they are not linearly dependent there. If they are not linearly dependent there means on interval I. So what happens in this case? In the previous case, for dependent case, we were able to find constant c1, c2 to cn not all 0, such that this linear combination is 0. Here, this is not happening. Converse. So that means for any type of linear combination which is 0, all the constants must be 0. Okay, that is if c1 f1 of x plus c2 f2 of x plus and so on cn fn of x equal to 0, then we must have c1 equal to c2 equal to and so on equal to cn equal to 0. We don't have any other option in this case. Okay, so all the constants must be 0 in this. Now, what is the relation between linearly independent functions and fundamental set? Let us see the result. Result is if y1, y2 and so on yn is a fundamental set of solutions of L of y equal to 0, on an interval I, then y1, y2 and so on yn are linearly independent. On interval I. Converse is also true. That means if we have linearly independent solutions on interval I, then they form fundamental set of solutions. Conversely, if y1, y2, and so on, yn are linearly independent, solutions of L of y equal to 0, then they form a fundamental set of solutions on interval I. Okay. In the next lecture, we consider homogeneous differential equations with constant coefficients, and we explicitly find out the general solutions in each case. Thank you.